Okay, good morning, everyone. Again, welcome to CNG 3351. And today, this is our fifth lecture. We're talking about the geometric design for highways. And geometric design, we're going to be mainly talking about vertical alignments and side distances, as well as horizontal alignments for the next few lectures. So today's learning objective, we want to make sure that we need to explain well the principles of highway alignments, and then we need to explain the what's the concept of stopping side distance. We talked a little bit about it last chapter, but we're going to expand on this concept this chapter. We also need to design the side distance or the stopping side distance and how it's related to the crest vertical curve versus the sag vertical curve, as well as explaining if we are designing a passing or an underpass side distance, how would this affect? So basically, we're looking into many cases of vertical alignments and how can we design those ones. And when I say again vertical alignment, it's basically which is different than horizontal alignment. Horizontal alignments, if you are looking at the roadway from an airplane and the roadway looks like this is here where this is the horizontal alignment. Basically, how are things uh, again? It's not again the roadway is not straight. There is some um, curvatures in that road. But if you're looking at the cross section alongside the roadway and how it's going up and down. And now let me give you even a more easy way to. So the car is here. Now it's moving up and down in this roadway. This is what I meant. This is what I mean by a vertical alignment. So the vertical curve or vertical alignment. It's if you are taking a look at the car from the side of the roadway while. So this is the vertical alignment, and this is here if you're looking from a plane and you see how the roadway can be a zigzag. This is the horizontal alignment. So first, again, we need to define, okay, what do I mean by geometric design? So that's the physical property of the facility. Any facility, when I say facility, it's the roadway mainly, and geometric design here is it's all about the geometry of the road, whether again horizontally or vertically. There are main elements of any highway geometric design, and this can be a career by itself, by the way, guys. So being a geometric designer, I know many students who graduated and most of their daily job is to do a geometric design, which has to do with designing the cross section of the road, the horizontal alignment, the super elevation, the vertical alignment. If needed, we can do even channelization at grade intersections, all the way to roundabouts and traffic calming devices that we can design and discuss. All of these are part of being a geometric designer, and those part of the elements of the designing roadways from the geometric perspective. So part of it also, again, we need to determine specific design elements. If you are a geometric designer, you need to end up designing how many lanes per direction. Very big question that need to be answered, and we're gonna get to learn this within this class and even next semester class, where it's all about the traffic amounts, but also what's the side distance and so many other factors that get it into the way. Besides the number of lanes, also is the lane width. Most of the or the typical lane width, if you have enough right of way on the sides, lane width is about 12 feet. Where in some local streets they can go all the way down to 9 feet in some cases. But we need to design that as part of the geometric design of the facility. We also need to decide what's the median type, if any, and what's the width of that median. If there is any lane, if there is any acceleration or deceleration rates lanes. Sometimes again we reserve the right lane on some highways, especially if they are going downhill for deceleration rates for trucks. Sometimes again, except an 18-wheeler, you are going downhill, and if the driver for some reason or another it's icy condition and he's losing or she's losing control, they have that deceleration rate where imagine now you're going a big again, a big old truck, and it's going downhill. So now what we do, we do something called deceleration lanes, where it's the right lane, it's designed for this, and then if the driver decided that, well, I'm really losing control here, so they're gonna take that lane, and then it has some sandbags and whatever it takes here just to absorb, um, if absorb the impact if the truck is really is again the driver is losing control. But again, you need to design that. You need to design what's the length of this decelerating lane, if there is a need one, if there is a need for one or not. Also, does I need to design one on and off ramps? Do I need to have again truck climbing lanes? That's also important, which is the opposite to the deceleration rate. The climbing. So now, assuming you are going uphill here, and again, it's another big truck, and if there is only one lane per direction here and you are behind that truck, you're stuck for a long time before, because now the truck is climbing this uphill, which in a significantly slower speeds than regular vehicle. So we also sometimes need to design a right lane just for that truck to use until it reaches the top here, and then going downward, that lane will disappear. So all of these again are elements that it's part of determining the geometric design. But we need to keep in mind that the major objective to design highways, that they have to be very safe, safe for wide variety of vehicle performance as well as wide variety of human performance. So again, we have lots of models of vehicles as old as, I don't know, 1930s or 40s or 50s, and we have up-to-date vehicles. So we need to make sure that our design, our roadway, will handle a safe experience for all kinds of vehicles. But also we need to have more what I like to call it a forgiving highway. That's the concept nowadays, where we try now to design that roadway to handle many human performances. I'm not gonna build a roadway that's gonna be for someone who is 100% concentrated, super young. The reaction time is way less than the recommended ASHTO time, which is 2.5 seconds. I need to have features, and I need to have the design factors in this highway that can have a good variety of human performances, even if that human who is driving that vehicle is not in his or her best emotional condition or psychological conditions. I would still like to have that safe facility to handle all kinds of people. Two questions on the chat. Is cost determining factor when it comes building a roadway with multiple ways, or does the need outweigh the cost? Very good question, Ethan. Um, it gets into the way. No, the cost also will be considered. But as I mentioned in chapter one, as a traffic engineer or as a transportation engineer, safety has to be number one. But after you qualify and after you make sure that the structure is 100% safe, you still end up having multiple design options, whether they are very costly versus not that costly. For example, and again, well, you're not jeopardizing the safety. For example, I can design a roadway with 2 lanes per direction or 3 lanes per direction. Both of them, you can design them very safely, but if you have the cost, if you have the funding, you would like again to expand the facility having 3 lanes per direction instead of two. But of course, safety comes number one, but after that, efficiency, or what we call cost to benefit ratio. You need to know what's the benefit of what you're designing versus what's the cost. And if you do the ratio, and if you prove that adding a certain element will improve the experience, and besides safety, of course, that can also get approved. But it's a it's an art being an engineer, and trying again to satisfy the safety, but also being efficiently economic. Good question. Um,
Yeah, that answered what I was thinking, because I was wondering if that was the case, because there's some roads. I mean, Texas is a little bit different, I feel sometimes, but like where you would really wish there was a passing lane, but there isn't, you know? And that
Yeah.
really, my next question is that the money for revising previous road names where they see maybe the design wasn't the full function where it should have been, where is that? Is that supposed to come from the gas tax, right?
Yes. Yes. And if you are referring to a specific example like the loop, the bigger loop that we have here, and yes, it needs more further improvements. Toll roads, they are funded by two ways, which we mentioned in the first chapter. Again, they are funded by taxpayers, but also you're paying money literally to use the facility. So those goes to improving that, but sometimes it take a while to see that improvement. They are trying, and instead of adding again, and they are going into cost, back to cost, where instead of adding a lane, they are thinking how about raising a median between the two directions. So if I'm a good driver, I don't need to be scared of the opposite direction, and if someone is gonna come and hit me, even if I'm the best driver ever. But of course, it's a priority list that the engineer will always put in front of the table or on top of the table. But uh, sometimes, again, it takes a little bit longer to realize that. But again, safety, always keep safety number one.
Thank you.
Of course. All right. So, what's our get go resource here for geometric design? This is very important, and this is the policy that's come from AASHTO. We got to know what's AASHTO last time. AASHTO is the American Association of State Highway and Transportation Officials. The book title says it's a policy on geometric design of highway and streets. The edition that I have here is the sixth edition. I don't know if they came up with new one, but it takes 6 years to come up with new ones. This book we call the Green Book. It's pretty much again this is the Bible for the designing geometric design for highways and streets. It's a very comprehensive, very thick book. It has everything that you could think of that we're gonna discuss this semester, and it's good to have it and use it as a good reference. All right, so let's define here some parameters that we're gonna use. First, when I mentioned to you earlier, as a geometric designer, you need to design the cross section. What do I mean by cross section? So basically, here we're referring here to the profile of the facility, which is actually perpendicular to the center line or the travel direction, and extends, of course, to the limit of the right of way within each facility that is constructed. Let me show you a picture. A picture is worth more than 1,000 words, as they say. So this is the picture of a cross section. If I were to cut perpendicular to your travel direction, this is the cross section. Many of us, maybe before this class, think if I'm an engineer, I'm going to design this little piece right here in the middle. This is the pavement. This is just the driving lane. That is not the case. You are responsible for the whole width from here all the way to there. That is all yours, which is the whole thing is what we call ROW, right of way. Right of way, or sometimes we call R or R/W. Basically, this is the whole area that the state or the federal government will aspire to have a control over. So I can have some area within my structure to expand in the future if I need to. For example, if I'm driving from here from Tyler to Dallas and they're on I-20 and there's 2 lanes per direction, who said we may not have a 3 lane per direction soon, maybe in 5 years or 10 years, depending on the need. But the right of way will give us that capability. The right of way, it can be on the sides, like in this picture here, or it can be within the structure. Again, back to the example of the I-20 where I have 2 lanes per direction and there is a big wide median in the middle. That's smart too. So now we are owning or the state or the DOT is owning the area between the opposite lanes, and all what they need to do if they want to expand, they're just gonna have 1 lane per direction using a little bit of that median in the middle, and that's an expansion. So, but the cross section is actually the pavement. which is again, regardless of how many lanes per direction, this is in one direction and this is the opposite. And I have a shoulder that me as a transportation engineer, you will be designing the shoulder. You need to be designing the drainage that goes so to get the water off the surface of the pavement as soon as possible. It's not safe to keep the water and it's not good to keep the water. Water is enemy number one for asphalt pavements. And we're going to talk about this towards the end of of this course. Again, my research area is in pavement design and pavement material, and water is not good to stay on the surface. So we're gonna, as a, we need also you. It's either you as a traffic engineer or you will be dealing with a water management, wastewater management engineer to design drainage. So that's what we call here the clear zone. And then, of course, as I said, you will acquire an additional right of way as needed, just for future expansion. So that's basically what it is. So we can have medians, barriers if needed, ditches or curbs. Arterials can also be at grade or elevated or depressed. So let me show you here some pictures of medians. So the first picture here, this is somehow similar to if you are driving to from here to Dallas. Of course, it's not as greenery as our lovely East Texas, but it just gives you the idea that we have two lanes per direction. We have a wide median in the middle, and then that median again can be at grade or it can be. Sometimes we design it to go a little bit lower. Sometimes we use it as a drainage or keep the water off the street. But eventually, the main the main reason for having a wide median is in the future. Okay, I'm gonna have a third lane here and I'm gonna have also here a third lane going this direction, while I still have some median in the middle. When things go like this, which mean now more traffic, which mean now this location is not as rural as it looked like, and now it's becoming more of an urbanized environment, and all of a sudden now the median become very thin, almost like again just a steel barrier or a concrete barrier at some locations, like again in this picture here. And if there is enough space, again we can have a median, but that median is way narrower than what we see in a rural setting. We can have barriers also, again, can be super thin like what we see here, very thin barriers. And again with all those barriers also, um, they are used and we see them on big highways. We also need to think of again curbs and gutters and ditches. That's also important, and it's part of us designing it. Sidewalks and crosswalks is very important. There is big demand now on how can we provide for pedestrians a good environment to walk or to bike. So that's also part of the cross section. If things get really crazy and lots of traffic going on. Again, we get to see now lots of elevated highways like what we see here, or we can go all the way to what we call the spaghetti design, where we have now multiple layers. Uh, Basically, we're trying to separate every single possible movement of traffic in one layer at a time. Or we can have depressed style like this. So you are driving. This is the main highway. It's continuous, and then if you really want to have now little roads on top of it, that's fine. We can do that. And again, if you really want to see more pictures or more examples, again, look at texasfreeway.com. I think it will have more of these pictures. All right, so a couple more pictures here related to our major topic. Besides, with all respect to what all the items that we talked, a major part of being a geometric designer or a transportation engineer is to design both horizontal and vertical alignment. Um, I always say here we're blessed in East Texas not to see crazy roadways like this, but I did drive on some of these mountainous roads when I was a research scientist in Reno, Nevada, University of Reno, Nevada, and I used to go visit friends and go again to Sacramento, California. So from Reno to California, from Reno to Sacramento, we're going through Lake Tahoe, for the ones who know the area there, and it's very mountainous, and you do not have that much of sight distance. You see those kind of streets. I tried them, and I'm pretty sure some of you already did, and that is an art to design such a roadway. If you ever wondered why we do not have much straighter roads, why don't we cut in the mountains? Again, it's very costly. So the to solve the problem is we need to study the horizontal and vertical alignment equations to still have a cost-efficient roadways, yet safe one as well. How can I have enough sight distance for those drivers so they know and they could see a danger well in advance, and then they can react to it at the right time. So this is here some pictures how things again. Um, from the plane view again, you can see this roadway is not exactly straight. Same thing with this picture right here. So let's go ahead and see again how can we design those roadways. Any roadway like what you see here, this is a 3D picture or a 3D situation, if you will. I mean, those pictures, no, they are not 3D picture, but you know what I'm saying, that the every roadway is actually a 3D problem. And for us as civil engineers, we like to change, or we do not like to look at this shape right here. For the ones who took statics or other courses, for some reason, civil engineers, they like to not to look at a 3D picture, and they like to simplify things. Same thing we're gonna do here. A roadway is a 3D problem, but now we dissect it, if you will, into two situations. We have the plan view, which is this is show you the horizontal alignment, and then we have the profile view, which shows you the vertical alignment. If you combine these two together, it's gonna get you the 3D picture one more time. But again, we tend to look at each roadway from two different views. One is the plan view, which is the horizontal curves and horizontal alignment design. And then also, if I look at the profile, this would be the vertical alignment and vertical curve design. A little bit of rough um, ideas here, or rough principles about surveying. So highway positioning defined by distance along the horizontal plane. So stationing, when I say stationing, again, with station being at 100 feet or 1 kilometer, depending on the units. So for example, if a point is at this much, which is 4,250 feet, which is in meters, is 1,295.3 meters from the origin. This station, then it can, the way in surveying, we do not put the distance as 4,250 feet. Oops. We put it in hundreds of feet. So it's 42 plus 50. What does that mean? It's actually 4,200 plus. After the plus, this is the rest of the feet, which is 50. And that's why, again, it's 4250. So that's why it explains this for you. Every station is 100 feet. So here when I'm saying this number, 4250 feet, is actually 42 stations. And that's why here we're saying it's 42. This is the number of stations, plus now this is the rest, which is plus 50. 50 is not 50 stations. 50 is 50 feet. So really 40, that's why here I said it's 42 stations times 100, because I know every station is 100 feet. That is 4,200 plus 50, and that will be 4,250. Same thing when it comes now to the metric units. If it's 1295.3 like this, how can I change it? If I know that each station is one, then again, that 1,000 only have one full station, which is 1 plus 295.300. 1, that's the number of station, and the rest, which is not even getting close to a station, that's the rest. So what you say is, what you see is, you see the one times 1,000 or times 1,000 to get a kilometer plus 295.3, and that's what's gonna get you to the 1295. All right. Let's now go to the, this is now really the meat of the presentation, if you will, for today, the vertical alignment. Vertical alignment, which is again going upward and downward. Remember, vertical alignment is the profile of the roadway. Most of the time, we will be designing, or we design in real life, equal tangent vertical curves. What does that mean? That means we are designing roadways that this is the roadway itself, and I'm thinking here like this is like the radius of the curvature, and no matter where you go, it's an equal tangent. That means from the beginning of the curve till half of it, this tangent is equal to this tangent. So if I'm driving on this roadway and going uphill and then going downhill, this is what we call a crest vertical curve. Crest vertical curve is again going up and down. Going up and down. You see, I want to explain for you this now. This is the positive G1. What do I mean by positive G1? Going up in vertical alignment was always positive. Going up. So plus G1, this is the first grade of this vertical alignment is positive because I'm going up until I reach this point here, and then I'm going down. Going down here, it has a negative G2. So if I am having a positive, then negative, this is a crest vertical curve. Or another case of defining a crest vertical curve, if it's a positive G1 and then a positive G2, but G1 is more steeper than G2. If G if positive G1 is more than positive G2, that is also a crest vertical curve. Or I can be driving on a negative G1 and then a negative G2, but the negative G2 is more steeper than negative G1. So a negative G1, and let's put it here now in an absolute value, is less than the negative G2. All three cases, if it's plus, then a negative, or if it's a positive, high positive, or a steep positive, then a lower steep positive, or if it's a negative, a steep negative, then a lower, less steep negative. All three cases, we call them crest vertical curve. The opposite to this is the sag vertical curve. Sag vertical curve, it's either a negative grade, then positive grade. So I'm going this way. That's a sag vertical curve, or a negative, steep negative, and then less steep negative slope or grade. So again, minus G1, this is higher than minus G2, or another sag vertical curve, it can be defined as I'm going positive, small positive, and then steep positive. So the G1 is less than G2. All these three cases will define for us or a sag vertical curve. Any questions on the definition here? All right. So let's define now more of, again, you've seen what's PVC, what's PVI, what's PVT, and what's L over 2. Let's define all of these in this picture right here. So this is the real curve that's gonna be constructed in the field. while those dashed lines are just imaginary in our on our design books to help us design this vertical curve. So let's start with this small simple thing. G1, capital G1, this is the initial roadway grade in percent. Remember in chapter 1 and 2 where we don't like to talk about theta, we like to talk about G, the grade. So the grade is in percent. For example, if I'm going upward at a 3% grade, again, that means I'm climbing 3 feet every 100 feet in the horizontal direction. That's a positive 3% grade. So G1 is the initial roadway grade in percent. G2 is the final roadway tangent grade in percent. A, you're gonna ask why we're defining this. Those are all the terms that we're gonna be using in the calculations later on. But A, this is the absolute value of the difference in grades expressed in percent. So A is G2 minus G1. Common mistake here. That negative will stay. This is part of the equation, but you need to keep the the sign of G2 and G1 as they are. For example, in this situation right here, we have negative G2. So the A now is gonna be, let's give you a numerical example. So this is easier. So plus G1, let's say I'm going upward here at plus 3%, and I'm going downward minus 5%. What is the A value? The A value now is gonna be the absolute difference between G2, which is minus 5, minus G1, which is 3. In this case, that's A is going to be now 8. Minus 5, minus 3. Any question how to get the A? It's the absolute value. And again, every grade is going to bring its own sign, but remember there's a negative or a subtraction in the middle here. For example, let me give another one before we get going. So if I have now a sag vertical curve, and I have minus 2, and here I have 4. What's the A value? The A value in this case would be A equal to G2, that's the equation, so which is 4 minus, that's part of the equation, and then G1. G1 is negative, minus 2. Therefore, A will be equal to 6. All right. Besides that, the beginning, so what's PVC? PVC, this is the point of the vertical curve, or the beginning of the vertical curve. Before that point, we're assuming that there was no vertical curve. It was, the roadway was flat, and then now we're going uphill or downhill. The PVC, this is the beginning of the vertical curve. The PVI is actually the point of vertical intersection, or what we call, again, this is the intersection of initial and final grades. This is an imaginary point. It doesn't exist in the field, but this is where the two tangents meet at each other. PVT, which is right here, PVT, this is the point of a vertical tangent. That's the name of it. Point of vertical tangent, again, this is the end. In fact, in reality, this is the end of the vertical curve, and supposedly after that, it's actually flat. If you look at the profile, before the PVC, it's flat, and then now the beginning of the curvature, and then we go downhill, and we reach PVT. This is the end of the curvature, and after that, the roadway is also flat. The last thing here we need to explain in this picture is the L, the length of the curve. The length of the curve is actually, it's in a station, and it's measured again in a constant elevation in the horizontal plane actually. So the L is measured in the horizontal plane, not along the curve. So that's something also I want to point out. The length of the curve is not the length of the curve is not along the roadway. It's actually the horizontal dimension, horizontal distance from PVC all the way to PVT. And most of the time we try to express the L in stations. For example, if the L is 600 feet, I'm not going to say L is equal to 600. I'm going to say L is 6 stations. It's going to be 6 stations. All right, let's get going with some equations. Those are equations that we need to understand, and where are we getting the final equations that we're going to use in the design. For vertical curve, as you see in the picture on the top here, a vertical curve, if you think about it, this curvature is actually following a parabolic equation, like what we had in mathematics, not even Calc 1, it's before Calc 1. Y is equal to ax squared plus bx plus c. That's as simple as that. Y in this case is going to be actually the roadway elevation at distance x. Imagine now I'm going this way, I'm going upward and downward. And now if this is the beginning of the curvature, I'm going to say, you know what? This is y, this is x, and this curvature can be easily explained by a parabolic equation. Then that's going to be easy because now the y is going to be now the road elevation. If I'm going upward or downward, this is the y. How am I going to get this? Using the y equation. Whereas the x in this equation will be now the distance from the beginning of the vertical curve in stations. So the x is going to be from here. Again, those are stations. Every station, I'll be now, okay, this is the x, and then I can go up, and this is the elevation. So the y is the elevation, x is the station along the vertical curve. All right, so we got the x, we got the y. Now, how can we get these coefficients? Because really, in order to solve any elevation or a horizontal distance at this vertical curve, I need to get the coefficients in order for me to define the equation. And after that, I'm done. I can have the equation. And then if anyone asks me, okay, what's the elevation or what's the distance and the elevation of any point, I'm going to apply A, B, and C, and I'll get the Y. So the A in this equation right here is G2 minus G1 over 2L. G2 minus G1, regardless of the sign again. G2 can be negative or positive, same as G1, over 2L. 2L, this is again the length of the vertical curve in the horizontal direction times 2. The B factor is right here. Simply is the G1. The B factor or the B coefficient is G1, the initial curvature or initial grade of the horizontal curve. C, this is now the elevation of the PVC point, the beginning. Imagine again back to uh, calculus. So if I'm doing, this is the curvature right here. If I am saying, if I'm saying that x is equal to 0, so let's see here. This is y, this is x. And now, you know what? I'm going to go to this equation. Y is equal to x squared plus bx plus c. How about if I put x equal to 0? If x is equal to 0, this is going to go, and that's going to go. And now y, the elevation at x equal to 0 equal to what? Equal to c, which is right here. This point here, this is c, that's why I'm defining it as this is the true elevation of the PVC, the beginning of the curvature of that horizontal, of that vertical curve. So that's in case of x is equal to 0. Any questions on this? All right. So another one more another aspect here is what we call offset. So back to this picture again. This is the beginning of the curvature at PVC, and I'm going uphill and I'm going downhill here. And then this is the reality in the field. But then I have, like what I told you while I'm designing, I'm having imaginary tangent to the first curvature and another imaginary tangent to the second curvature. And they are meeting at PVI. What do I mean by offsets? Offsets are the vertical distance, actually. from the initial tangent to the curve. So at this point here, there is no offset. There is no difference in distance between the real line, the real curvature, and the tangent. But by the time I move away from PVC, I'm going to start now generating what we call the capital Y. Capital Y, this is the offset. The offset will keep increasing until I reach what we call YM. This is the maximum offset, which is the maximum distance between between the highest point on the curve and the PVI. And then if you extend this line, you're gonna get what we call the final offset, which is the distance between the PVT, the end of the curve, and the extension of that tangent. How can we get all these equations? So for an equal tangent parabola, is again, the y will be defined as follows. Y is equal to a over 200 L times x squared. X is easy. That's the horizontal distance. If I want to know the offset at any single point, I need to know what's at what distance. L, that is defined previously. This is the length of the vertical curve in the horizontal direction. And A, I hope you still remember, that's the A right here. Please make the distinction. There are two A's here. Capital A, this is the absolute value of the difference in grades, which is G2 minus G1, while small a in this equation is G2 minus G1 over 2L. Please make the distinction. In this equation, you are using capital A, which is the absolute difference between G2 minus G1. This is the general equation that you can get the offset at any point along that vertical curve. But there are simplified equations for offsets at certain points of interest, which we typically report in any design project. Ym, this is the offset at the curve midpoint, which I just pointed out here. So this is the maximum or the midpoint offset. Let me take this back. So let's say this is the midpoint offset. And Yf, this is the offset at the end of the curve. Ym is AL over 800. Yf is AL over 200. Those equations will be provided to you again in an exam if needed. But not this equation. This is a parabolic equation. Everyone knows it. I'll be providing you what's A, what's B. The C again, it's just the elevation. But the parabolic equation, everyone should know that way before even joining university. All right. Another factor here, and bear with me again, defining all these factors, and then we're going to go through problem solving in another session. But the K value is defined as L over A. L, this is again the length of the curve over A, the absolute difference between G2 and G1. In another term, K is actually, again, this is a value that's the horizontal distance required to affect 1% change in the slope of the vertical curve. Let's read it one more time here. If you think about this is a ratio, L over A. L, it's the length over A, which is percentage of grade. So K, again, is the value that is the horizontal distance required to affect a 1% change in slope of the vertical curve. Capital A, we got to know again, G2 or G1 minus G2. And L, this is the length of the curve in feet or meters. Why do we care about the K value? The K value, actually, it can be used directly to compute the high as well as the low points for a crest vertical curve as well as a sag vertical curve. So how can we get this? We get it using this simple equation right here. X HL, this is again, this is the distance from the PVC to the high or low point of that curve. It's equal to K times G1, the absolute value of G1. So K, which is L over A, times G1, that is going to be equal to the XHL, which is the distance from the PVC to the high and low point. Additionally, again, I'm going to show you that the K will be, it's one of the important applications is to design the vertical curve that I'm going to show in a little bit. Those problem statements or problems that we are going to have a designated lecture before your first exam to go through example 3.1, 3.2, 3, and 4 to discuss and use the equation that we discussed today. All right. Now we've talked about the original equation that was used, which is the parabolic equation. Now, how can we link the side distance, the stopping side distance, to the curve design concept? Because with all respect to both concepts, they have to talk to each other. If I'm designing a vertical curve, I'm going uphill and I'm going downhill, and I really need to see what's going on in front of me. If there is something dangerous happening and I need to stop, I need to have enough side distance. And that side distance is always related to the length of the curve. For example, if I'm going upward in this curvature right here, so the car is going upward, it's very steep, I'm going this way, the L is small, but I don't have enough side distance. Sometimes even the L, if the L is less than the stopping side distance, that's a problem. Versus if I want to make this curvature smoother, and now the vehicle is right here, and now the L is longer, and now I can see much. So if there is a danger here, I can see it, but if there is a danger here, I cannot. If the L, your goal is L will be more or equal to the needed stopping side distance. So I hope you see now why we care about these two concepts together. It is necessary, as I'm mentioning here, again, when designing vertical curves to provide adequate stopping side distance, because again, curve construction is very expensive. So when we're designing those curves, which is very expensive, so we really want to minimize the curve length as much as we can. Think about it. This here would require less cutting in the mountain compared to this one. The bigger L, that means I need to cut more. It's going to be more expensive. So, but always we have to put safety first. That's why we're always comparing the L, the length of the curve versus the side distance. So while we're doing this, we need to think of selecting, designing, and locating the final alignment of the facility to connect the 2 points is highly complex, very important. How can I connect this point to this point to the top of that vertical line? Very, very important. Why is that? Also because it's gonna affect our cut and fill. For the ones who took surveying, if I am designing multiple vertical and vertical alignments, something like this, just again a hilly area going up and down, and now this is not good. Now you're saying, you know what? I'm gonna try to cut it and do something like this. This is the mountain, very steep. And now this is your suggested roadway. What's going to happen? In this, so this is the suggested roadway. I need to cut the mountain in this area. I need to cut this big area. And I need to cut this area as well. And guess what? In this area now, I need to fill, and I need to fill this area. So when you're designing multiple vertical alignments along the way, you would need to think of that as well. How can I manage the cut and fills? You would like not to have too much cuts because that's going to be a lot of money to cut through the mountains all over. And you would not like also to have lots of fills because otherwise now you would be requiring to buy good materials from elsewhere, haul it to your location, compact it before you start paving. And that's also expensive. So you need to really manage between the cuts and fills to have minimal cuts or minimal fills, or at least minimal. The balance has to be there. Otherwise, it's going to be a costly undertaking. So the general objective here, we need to minimize the borrow cost as well as the overall cost. This is very important. And but again, sometimes we end up with resource limitations. Again, economical or legal or environmental constraints. So all of these has to be considered. While of course on the top of the list is safety and how can we maintain the enough side distance for every location. So let's bring you back to chapter two. This is the equation that I hope it's not new to you by now. This is the side distance, and instead of we didn't used to call it side distance, we used to call it the big D. Remember, that's the D plus the dr, and this is ds, I think. So instead of ds, now in this chapter it has a new name, stopping side distance. Stopping side distance is equal to v1, your original speed, squared over 2g times a over g, plus or minus capital G. I hope you know that by now. That's the grade, plus v1 plus tr. Again, v1 plus dr. This is the dr, the reaction time. Just before you hit on the brake, you're still traveling at your original speed, and it's taking you some time. I hope you remember what was the recommended tr. Anyone remember? The TR, the reaction time recommended by ASHTO, a conservative number, 2.5 seconds,
2.5.
2.5 seconds, yes. So TR is 2.5 seconds. And again, based on ASHTO, as I'm mentioning here. So really, what ASHTO did, instead of us, as again, if you are a geometric designer and you're doing this on a daily basis, and you're always checking the length of your curve versus the side distance to come up with this desired case that the length of your vertical curve is more or equal than the SSD, you don't want to go every day and calculate the side distance. So what Ashton did, which I'm going to show you in a second, table 3.1 gives you now the side distance values in 5 miles per hour increments based on the equation that's used by Ashton right here. So let me show you here so it's more revealing to you. So this is an table from Ashton. You can use it, you can cite it. So it's actually giving you the side distance based on the speed limit of the roadway. Why is that? Because take a look at this here. What's really changing? What's changing is minimally the grade, which we got to know the grade is it doesn't change that much, maximum 5% or so. But really the bigger factor, if I'm assuming that TR is 2.5 seconds, the deceleration is fixed by Ash to 11.2, or acceleration 11.2. The G is 32.2 if you are in the US, or 9.81 if you are outside the US. So really what's changing, if you think about it, is just the V, which is the speed limit. So that's why Ashto came up with this table right here. Based on your speed limit, let's say I'm designing a new segment on I-20 and the speed limit is 75 miles per hour. Let's go here, 75 miles per hour is going to give me the brake reaction distance, which is the dr, if you remember, is 275, and the braking distance on level, that's the whole, that's again that's the braking distance, which is now once you push on the brake, that's 539.9. If you sum up the two, the calculated stopping side distance is 815, and the design is 820. What does that mean? The design, again, was just the design. At the end, as an engineer, I'm not gonna provide the contractor. You know what? I need a stopping side distance equal to 815.5 feet. He's gonna laugh at you, and he's gonna know that you're a newly graduated engineer. You always have to pump it up a little bit to the higher side. In fact, to the nearest 5 feet. That's why again, 815.5 is gonna be 820. This is really the main column right here. This is the design stopping side distance. So if you think about it, again, it's a nice little table. You don't have to calculate the stopping side distance every time, and it's available for you. Even if you get to work overseas, you're gonna use the other half of the table right here. If you are again designing a roadway at 100 kilometers per hour, you got the braking distance, you got the brake reaction distance and the brake distance on level, and then the calculated, and this is the design number. What does it mean if you're, some of you may ask, what's the braking distance on level? This whole table is actually one of the assumptions is built on if it's a level, the G is almost approaching zero, which you're going to say, okay, no, but ours is maybe 2% or 3%. Again, the difference is between, again, a 0 and 1 or 2 or 3% is minimal. And part of the whole calculation of having a bigger reaction time, and pumping the number anyways at the end to reach again. So those designing numbers is including inside them there is some sort of a cushion or a design or a factor of safety to handle that this simple assumption from G is equal to 0, maybe to G equal to 2 or 3 or 5%. Any question on table 1? All right, let's talk now about the stopping side distance and crest vertical curve design. All right, so here, take a look at this. We are going to be designing vertical curves, either if they are sag vertical curve, they have their own equations, and if they are vertical crest vertical curve, they have their equations. So let's start with the crest vertical curve. How can we design these? So take a look at this situation. You are driving on this curvature, and really there are two major factors, if you think about it, that can affect the design of this vertical curve. First is the driver's eye height, which is h1. When you are sitting here, this is the height of the eye of the driver, h1. And the second factor is h2, which is the height of the roadway obstruction. You're driving and everything is nice, and then you see something on the roadway that it's making you have to stop. H2. Why it's that small? Or again, if it's a big obstruction, it's gonna be seen from far away anyways, and that's actually not the worst case scenario. That's why you may think, why H2 here seems so little? It seems so little because you are designing the roadway for the worst case scenario. The worst case scenario is there's something very small on the roadway. It's hard to be seen, yet you need to make sure that the driver is seeing it. That's why you're designing the roadway to have enough sight distance for small objects, not for big objects. Because big objects, again, if you see a big crash in front of you and there's a couple cars is being involved, you see it from far away, and that's not the worst case scenario. We're designing those roadways for the worst case scenario. So it all depends on H2 and also H1. How high is your how high is the eye of the driver? And we design those roadways based on actually very low profile car. Because think about it, if you're driving on a truck, if you're driving a truck, the height of the eye of the driver is way higher, which means instead of here, it's gonna be here. So you really can see now a lot. You will be seeing, you can see much more, and you're gonna avoid any accidents in a much better case. So when we design the the crest vertical curve, we assume that the H1, the lowest profile car ever. So we are again accounting for multiple vehicles and multiple drivers. So where can we get now the minimum curve length? Remember, your goal as a geometric designer, you need to get the L. You need to get that L. And again, your goal is to have a length, the length of the curve is to be as high as possible. So using again the parabolic equation that I showed you before, and again, we're minimizing as the minimum size, the minimum length of the curve is actually using these two equations. Let's discuss the first one. For if the side distance is less than the L, if the side distance, that means the length of the curve is way more than the required side distance, you're going to use this equation to get the LM. What's M? This is the minimum length. Remember, having a bigger length, this is actually good, but it might not be very economical. So you're looking at the minimum length of the curve, not to be too steep. You're looking at the minimum length. The minimum length is all about A, which is again G1 minus G2 times S squared. S here, I believe this is the speed, and for some reason here they're using S, not V. So this is the speed over 200 times the square root of H1 plus the square root of H2, all this to the power 2. What's the H1? Again, this is the height of the eye of the driver, and H2, this is the height of the obstruction or the danger in front of you. In case of this stopping side distance is higher than L, then the minimum length is going to be now using this equation. And the typical question that I always hear from students is, which equation should I use? And the answer, simple answer, we typically start with equation 3.13, which is we're assuming that the length of the curve is higher than the side distance. So the side distance, already I will be having it from the table 3.1, correct? Table 3.1, that's available. You're gonna go here. Oh, I'm sorry. This is not the speed. I'll take that back. This is the side distance, SSD. This is the side distance. So if you know the side distance from table 3.1, you're gonna plug it in here, and you know the A, you know the H1, you know the H2, then you're gonna get the LM. If once you get that, you're gonna compare it now to your assumption. Is really now the LM, the minimum length, is higher than the SST that I put in the equation? If that assumption is right, then you stop your calculation. If it's not, then you're gonna use now the second equation, this one right here. You're gonna come back again, use the same table 3.1 SSD. You're gonna use this equation, and now you're gonna satisfy this equation 3.14 instead. Make sense? All right. So this is here again. Those serve as general equations. If if there is an accident happened, severe accident happened, and it's a very sophisticated case, you really need to get into what was the exact H1, what was the exact height of the obstruction. So you need to use these equations. If you are just designing a roadway and you just want to know what's the typical side distance and the length of the curve, the ASH2 actually are recommending H1 and H2. These are just general H1 and H2 for you to use in case you do not know the H1 and H2. So the H1, they are using the driver's eye height is 3.5 feet. 3.5 feet. Um, that's the height of the driver. You may say this is too small. I get it, and it is too small. But remember, AirStore is always designing for the worst case scenario. The worst case scenario, you're driving on a low profile car. The height of the driver is very small, so you can't really see much. So we need to we need to put it in the equation. Same thing with the height of the obstruction. 2 feet. Anything that's 2 feet and 2 feet, that's also very conservative assumption, because if you see something bigger, you're going to be able to spot it from far away, and that's good. But we're always looking for the worst case scenario. So what Ashton did to again make the life of transportation engineers a little bit easier, they took the previous equations and now they replaced H1 and H2 with the numbers that they're recommending, and that's what they ended up with, a simpler equation. For the US customary, if you're reading US customary units, for SSD less than L, which is again this is your desired case, LM now become a simplified equation, which is A times SSD squared over 2158. And for the if you apply this assumption, and if it doesn't, if it does, and then you do the calculation, you put the SSD times A over 2158, and now if the L is higher than SSD, you start your calculation. If the L is lower than SSD, you're gonna go to the second equation and apply this one right. If you are outside the US, of course, you're gonna use these equations. The third simplification. So again, these are now one simplification at a time. So this is the general equation. If you really know what's the H1, what's the H2, exactly, you need to apply this equation. If I give you in the homework or an exam, if I give you specific H1 and H2, you need to use these equations. If I did not mention anything about H1 and H2, and I did not provide anything, any H1 or H2, you're gonna jump now. We're gonna assume that, well, I don't have H1 and H2. I'm gonna use the Ashton equations, assuming H1 is 3.5 feet, H2 is 2 feet, and I'm gonna go with that. The third simplification is as follows. Since again, using this equation can be cumbersome, at least once you graduate and things now become slower and your mind is not as fast as what it used to be, tables now have been developed utilizing the K factor. Remember again the K, when I told you L over A, and you wonder what's the use of it. So we discussed it earlier, but now the use of it is right here. So for crest vertical curves, for US customer units, K is equal to SSD squared over 2158. That's the K value. So if I know what's SSD, I can get the K. And if I know the K, I will go here and I multiply the K times A. So now K times A will get me the LM, the length of the curve. And that's exactly what the next table is all about. So, but again, there is some specific rules apply for you to use this table. If the L is more than SSD, then the minimum length is equal to K times A. This is the table right here. Very simple, even simpler than before. If I know the design speed, let's say again 75 miles per hour, I know the stopping distance is that much. I know the K, the calculated K and the recommended K. So once I know the K, this is a simple table. Once I know the K is equal to 312. I'm gonna multiply this by A, by A to get for me the LM. Very simple. So the LM is equal to K from table 3.1 times A. The K here from table 3.2, I mean, times A. All what you need, again, what's the speed limit of that structure? And then you're going to get the K multiplied by A, and you get the length of the curve. But again, you need to know that this is only for specific conditions. If L is more than SSD, and we're assuming again that G is equal to 0. So just to summarize here, basically we have now this is the minimum curve for the crest vertical curve if I know the H1 and H2. If I do not know H1 and H2 for this specific incident, I can use the second category of equations, which are the simplified ones, assuming that H1 and H2 are following the AASHTO standards. H1 3.5 feet, H2 is 2 feet, and you can use these equations. Or even further simplification, if I know that the L length of the curve is more than the side distance, stopping side distance, I can just go to the table 3.2, get the K, multiply by A to get the minimum length. And again, for the ones who are still questioning which equation should I use, you always go with the first equation, assume that the SSD is lower than the L, go with the calculation, and then compare the SSD with the L, the minimum length that you got. If the minimum length is higher than SSD, great. Your assumption was right. If not, you're going to jump to the second equation, and that will be your answer. These are the assumptions again. As I said again, assuming that L is more than SSD instead of SSD more than L. So if SSD is more than L, then the relationship between A and LM is not linear, so the K cannot be used anymore. So please, if the SSD more than L, you cannot use that anymore. In fact, at low values of A, it's possible to get negative minimum curve, which doesn't make any sense. But if the L is more than SSD, then yes, you can use the table. Some other notes here again, table 3.2, assuming G is equal to 0, as I mentioned. Why we use this table? Because it's difficult to get the exact effect of the grade unless you know exactly where on the curve where the brake will be applied, and that's why we assume G is equal to 0. And we're assuming initial or final could be again too conservative or too risky. But the practice in this situation really varies. So most agencies that do not correct for this equation if the G is less than 3%. So if we have 0, 1, 2, 3%, that's fine. We use the equation, even if the table, I mean, built on G is equal to 0. But if it's more than that, we typically add a fixed distance correction to the minimum L. Because again, the minimum L is the length of the curve. If the G is now more than 3%, you still use the equation and then add, let's say, 100 feet or so. Some minimum curve length, just a rule of thumb that I've seen over the years, the minimum curve length LM is somewhere between 100 to 325, depending on the individual jurisdiction guidelines. But what I have seen, and it's a good rule of thumb, is this: the minimum length of the curve is 3 times the design speed if you are using miles per hour, and the length, of course, in feet. So, if, for example, if if the speed limit is 50 miles per hour, as a rule of thumb, the minimum L will be 50 times 3, and the minimum length then L minimum is around 150 feet. I'm not telling you to abandon these equations. You have to follow the equations, but sometimes actually it's the other way around. You use the equations and then you compare it to your rule of thumb and see, oh, well, okay, does this number make sense or not? If you are in other countries that you're using kilometers per hour and the length of the curve is in meters, it's 0.6 times the design speed. This is again just to give you an idea of a rough number or rough estimate of the minimum length of the curve. With that, we finished the first half of the chapter and actually the first half of this lecture. And next time we're going to be talking about this, the design now of a sag vertical curve instead of crest vertical curve. Thank you.